Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall study arguments of products and quotients. Earlier, we have seen what is the modulus of a complex number and argument of a complex number. If a complex number, suppose z, which is order pair of x and y represented in this form, or this can also be written as x plus I into y, or in polar form it is expressed as r into bracket cos theta plus I sin theta, or which in exponential form is expressed as r into e power I theta. So, in these two expressions, r is called the absolute value of z or modulus of z, and see, mod z is equal to r, or which has the expression under root of x square plus y square, and theta is argument of z, which is written in this form. And we know if theta is argument of z, then there are infinitely many values of argument of z, which is integer multiple of which differ by integer multiple of 2 pi, or this is theta plus 2n pi, where n is the value of any integer. N is equal to 0, plus minus 1, plus minus 2, etc. So, this is meaning of argument of z, and in this also we have considered principal argument, which is denoted by capital A R G Z, and this argument z is that value of theta which lie between minus pi strictly less than argument z is less than or equal to pi. That value of argument z, which is between minus pi to plus pi, is known as principal argument of z. So, this part we have studied in our earlier lecture. You may please see that lecture so that you can understand this, and that will be a revision. Now, here what we are going to study is arguments of product of complex number, quotient of complex number, and power of complex number also. Let z, z1, z2 be complex numbers, then the following results hold. First is argument of z1 into z2 is equal to argument z1 plus argument z2. Second is argument of inverse of z is equal to negative argument z. Here z must not be 0. And for third result, argument of z1 divided by z2, z2 is non-zero, is equal to argument z1 minus argument z2, and argument of z power n is n into argument z. So, these are the four results that we will prove, and to prove this result we shall use this form of complex number, exponential form of complex number, that is z is written in the form r e power I theta. So, we shall prove these results one by one. The proof for first. And we shall assume let z1, here we need z1 and z2, let z1 is equal to r1 e power I theta 1, and z2 is equal to r2 e power I theta 2, be two complex numbers. We have then z1 z2 is equal to, then z1 z2 is the product of these two, that is r1 e power I theta 1 into r2 e power I theta 2, and we know this is r1 r2 are positive real numbers. So, r1 r2 and this product e power I theta 1 into e power I theta 2 is written as, earlier we have seen this, I into bracket addition of the indices, I is common in bracket theta 1 plus theta 2. So, this is z1 z2, and thus z1 z2 is expressed as r1 r2 into e power I theta 1 plus theta 2. Now, z1 is this number, here argument of z1 is theta 1, argument of z2 is theta 2, and from this argument of z1 z2 is theta 1 plus theta 2. If a complex number is written in this form, r1 is the absolute value of z1 and theta 1 is the argument. So therefore argument of, and that is one value of the argument. There are infinitely many values of argument of z which differ by the integral multiple of 2 pi. So therefore a value of argument z1 z2 is theta 1 plus theta 2, and so all the values of argument z1 z2, therefore argument z1 z2 will be theta 1 plus theta 2 plus 2n pi, because if you consider multiple of 2 pi, that is 2 pi, and multiple of 2 pi, and the angle is increased by multiple of 2 pi or decreased by multiple of 2 pi, we get the same position, and therefore argument remains the same, and where n is equal to 0, plus minus 1, plus minus 2, etc. Any integer. This is the value of argument of z1 z2. Now we shall have argument of z1 is from this. Also we have argument z1 is, this is theta 1 plus 2n1 pi, multiple of 2 pi, and here n1 is integer like this. Here we have taken n1, and what is argument z2 from this expression? It is theta 2 plus 2n2 pi. n2 is integer, any integer. Now we shall express argument z1 z2 again. Now argument z1 z2 is equal to, it is see here, theta 1 plus theta 2 plus 2n pi, earlier we have written, and this now can be written as theta 1 plus 2 n1 into pi. In one bracket we shall write, plus into second bracket I shall write this as theta 2 plus 2 n minus n1 into pi. Now both are the same, because what we have done is we have added 2 n1 pi, we have subtracted 2 n1 into pi, and this value remains the same. And see, this is further. This we shall keep as it is, theta 1 plus 2 n1 pi, and this may be written as theta 2 plus 2, n is integer, n1 is integer, n2 is integer, and this n minus n1 is difference of two integer is an integer, and we shall denote it by n2 pi, where n2 is equal to n minus n1. And but now what is this first bracket is argument of z1, and the second bracket is argument of z, you see, and thus the result follows. First result follows, argument of z1 z2 is equal to argument z1 plus argument z2. So hence the first result. Now we shall consider the second proof for second result. What is the second result? We shall write here, proof second. Let z, here z is to be considered, and that is non-zero. Let z is not equal to 0 and z is equal to r e power I theta. This is the complex number in exponential form. What is the argument of z is theta, and therefore then what is the inverse of z? That is 1 by z, multiplicative inverse, and which is 1 over r into e power I theta, and this is written as 1 by r e power negative I theta. So therefore, what will be the argument of z from the 1 by z or z inverse? It is negative theta, because here argument of z is theta and instead of theta here is minus theta. So therefore, argument of z inverse or multiplicative inverse of z, argument z inverse is equal to minus theta. But what is theta? Theta is argument of z. This is equal to negative argument z, and this is argument of z inverse is equal to negative argument z. Now we shall consider the third result, argument of z1 by z2. Again here we shall suppose let z1 is equal to r1 e power I theta 1, z2 is equal to r2 e power I theta 2, and z2 is not equal to 0, because we are taking quotient and this is necessary, non-zero at denominator. Now therefore, argument of z1 is theta 1, argument of z2 is theta 2. Now we shall have their quotient, argument of z1 by z2, or that is z1 z2 we shall express first. z1 by z2 is equal to, this may be written in terms of multiplicative inverse, or this we shall write this as z1 into 1 over z2, or that is z1 into z2 inverse. And therefore, argument of z1 by z2 is equal to argument of z1 into z2 inverse, and that from the first result, it is argument of the product is sum of the arguments, and that will be argument z1 plus argument z2 inverse. And we know what is the argument of z inverse, negative z argument z, and this result is applied. This is by property 1 or result 1, and this is equal to argument z1 minus argument z2. This is by result 2, and this proves the third result. Now the last one, proof for see, this is what we have proved is third result. Now proof of fourth result. Let z not equal to 0, here not necessary, let z is may be any, let z is equal to r into e power I theta, and n is any integer or any power of z, and therefore see what is z power n is equal to r e power I theta, and that is raised to n. So this is equal to z power n. So n is any power, it may be integer or may not be integer, and that is z power n is equal to r power n e power I theta n, and this gives argument of z power n is equal to, so this is the argument theta into n, and that is theta into n or n into theta. And what is theta? Theta is argument of z. Thus argument z power n is equal to n into argument z. So thus we have proved all the four results for general argument. Now whether these results hold for principal argument, that we shall write as a remark, the result 1, taking result 1. See, the result 1, and hence all these results, the above results, may not hold for principal arguments. For example, the first result, if we replace argument by principal argument, and we know principal argument is that value of argument which lie between minus pi strictly less than the argument and less than or equal to pi. So for example, the result, first result is for principal argument, it is denoted by this notation, capital A R small g small, ARG Z1 Z2 is equal to principal argument of Z1 plus principal argument of Z2 may not be true always, or is not true always. One counter example we shall state here. So let Z is equal to say minus I or minus 1 and Z1 and Z2 is equal to I, that we shall consider. And see what is this Z we shall express this as, or we shall have Z is equal to 1 and Z2 is equal to minus I. Then Z1 is 1 into e power, say it is 1, so therefore we shall consider this as minus 1 and this as plus I, and this will be expressed as e power I into pi, because we know what is by Euler formula, e power I theta is cos pi plus I sin pi, and cos pi is minus 1, sin pi is 0. So therefore this is exactly minus 1, this value is exactly minus 1. What is Euler formula? E power I theta is cos theta plus I sin theta, or we have seen this earlier. E power I pi or negative real number has exponential form as in this way, e power I into pi. If it is minus 2, then it is 2 into e power I into pi. So Z2 and Z2, this is I, and therefore this is 1 into e power I into pi by 2, because cos pi by 2 is 0, sin pi by 2 is 1, and therefore using this formula this will be e power I into pi by 2. And therefore what is the argument of Z1? Principal argument we shall write directly, and therefore principal argument of Z1 is from this, it is pi, and that is within the range of principal argument pi. And what is principal argument of Z2? Principal argument of Z2 is pi by 2. Now we shall take their product Z1 Z2. Now what is Z1 into Z2? Z1 is minus 1 and Z2 is I. So therefore it is minus I, and thus this minus I is written in the form of exponential expression, and that is e power I into 3 pi by 2. Cos 3 pi by 2 is 0, sin 3 pi by 2 is minus 1. So my I into minus 1 is using this formula. So this is the expression. And what is the argument of Z1 Z2? Principal argument of Z1 Z2. So principal argument of Z1 Z2 is 3 pi by 2, or see, 3 pi by 2 is not principal argument because it is greater than say pi, and instead of taking 3 pi by 2, see the angle is, if you consider 3 pi by 2, it is here. Instead of taking angle in this sense, we shall consider it in this sense, and because to get the principal argument. So therefore the principal argument, or this I shall write as negative pi by 2, e power I into minus pi by 2, and thus the argument of z1 z2 is minus pi by 2. I is here and this is minus pi by 2, but this argument of z1 z2 is not equal to argument of z1 plus principal argument of z1 plus principal argument of z2, but see this is minus pi by 2 and this is not equal to argument z1, or we may write like this, but argument z1 plus argument z2 is equal to, this is pi plus pi by 2, which is equal to 3 pi by 2, and this is not equal to principal argument of z1 z2, and thus the result does not hold. Principal argument of z1 z2 is not equal to principal argument of z1 plus principal argument of z2. So the result hold for argument but does not hold for principal argument. So in this way we have seen arguments of products and quotients. Now we shall solve some problems on the results that we have just proved. Find the principal argument capital A, R, G, Z when Z is having these three forms. First we shall have solution for first. Z is equal to minus 5 divided by root 3 plus I, and therefore argument of Z is equal to argument of minus 5 divided by under root 3 plus I, and we have the result as argument of Z1 by Z2. We will now write as a small a because general argument, not the principal argument. The result we shall first apply for general argument, because the result which holds for this general argument may not hold for principal argument. We shall first find the argument of Z, and from this we shall find the principal argument of Z. What is the difference between argument Z and principal argument? Argument Z has infinitely many values which differ by integer multiple of 2 pi, and principal argument is that value which lie between minus pi to plus pi, and that is ARGZ. This is the value. So we shall find that value which lie between minus pi strictly less than that value and less than or equal to pi. So first we shall use the result for argument of quotient, and we know this is argument of minus pi numerator minus argument of denominator, that is root 3 plus I. And what is argument of minus 5? Argument of any negative real number is pi, because that is to be written as 5 into minus 1, and that is 5 into e power I into pi, and therefore the argument of negative real number is pi, and therefore this is pi minus what is argument of root 3 plus I, and that argument we shall write as its principal value. We have the formula as if this root 3 and 1, the order pair, and it lies in the first quadrant. So therefore if the point lies in the first quadrant, its argument is theta is equal to tan inverse y upon x, and therefore it is tan inverse 1 upon root 3, and that is minus tan inverse 1 by root 3. We have studied this in our earlier lecture, you refer that lecture. And this is pi minus, what is tan inverse of 1 upon root 3, and this is, we know tan 60 degree is not 60 but 30 degree, tan 30 means pi by 6, tan pi by 6 is sin pi by 6 which is sin pi by 6, sin 30 is half, and cos 30 is root 3 by 2, and therefore it is 1 upon root 3, and that is pi by 6. Tan inverse 1 upon root 3 is pi by 6, and this is 6 pi minus pi is 5 pi by 6, and because this value 5 pi by 6 is less than pi, and therefore this is to be taken as principal argument. Since we may write as like this, since this value 5 pi by 6 is between minus pi is strictly less than 5 pi by 6 is less than or equal to pi, principal argument of z is equal to 5 pi by 6, which is the principal argument of z, means minus 5 divided by root 3 plus I. So this gives the solution for the first problem, and second is similar to the first, you try yourself. See, for second, try yourself. The solution for second problem is answer is 3 pi by 4 for this. Now third, we shall consider solution for third problem, that is also simple, and that is z is, let z is here given, z is equal to root 3 minus I power 6, and therefore argument of z power n, the result we shall use, fourth result that we have proved, and therefore argument of z is equal to argument of root 3 minus I power 6, and argument of z power n is n into argument of z, and that is equal to 6 into argument of root 3 minus I, using result last fourth. And what is now the argument of root 3 minus I? The point root 3 and negative 1, order pair for this complex number x comma y. This belong to which quadrant? Root 3 positive, and this is negative, means it belongs to fourth quadrant, and in the fourth quadrant the formula for argument is tan inverse y upon x. First quadrant, fourth quadrant, the same formula is there, theta is tan inverse y upon x. For second quadrant it is pi plus tan inverse of y upon x, and for third quadrant it is minus pi plus tan inverse of y upon x, and therefore this is 6 into, this is argument z, I shall write here 6 into that is 6 into argument of root 3 minus I, and that is tan inverse of what is y is minus 1, and what is x is root 3, and as in earlier we have tan inverse of negative theta is minus, this minus sign comes out and that becomes minus 6 tan inverse of 1 by root 3, and as seen earlier it is minus 6, and tan inverse of 1 by 6 is pi by 6. Tan inverse of 1 by root 3 is pi by 6, but it is negative pi, and that is argument of what is this value is argument of this number root 3 minus I power 6. But we are asked to find principal argument, And to get principal argument from this argument, we may add here integer multiple of 2 pi to get the range between minus pi to plus pi. And minus pi is not to be taken as principal argument. So the principal argument lies between minus pi strictly less than and less than or equal to pi, argument z. So we shall add 2 pi here to get the principal value. Therefore, principal argument, that is capital ARG of root 3 minus I raised to 6 is equal to negative pi plus 2 pi. Add 2 pi, and therefore this is equal to pi. Now pi is permissible value for principal argument, not minus pi, and therefore we can add integer multiple of 2 pi, and that is 2 pi we have added to get the value. So this is the principal argument of root 3 minus I power 6. So in this way we can find principal argument using the results on arguments of quotient, product, power, etc. I hope you can understand this. Thank you for watching the lecture.